Hello everyone. It was really hot in Hume this morning. I'm serious when I said 90 degrees in that email. I just didn't figure you wanted to sit in that. No, I didn't. So I'm going to do this video to sort of take the place of lecture that we would have had today. So on Friday we did double integrals, which was integrals for multivariable functions. Today's section 8.2, partial derivatives. This is the derivatives of multivariable functions. So in Cal 1 and even up through the first three tests of Cal 2, we've worked with some derivatives here and there, even in Cal 2. If you had a function f of x equal, something, whatever it is, doesn't matter, then one notation you'd use for derivative was f prime of x. Likewise, instead of using f of x equal a function, if you'd used y equal, you probably used what's called Leibniz notation, which was dy over dx, to indicate the derivative. Since we're dealing with multivariable functions now, there are actually more derivatives. To keep things as simplified as possible, we're only going to deal with two variable functions. So for instance, f of x, that means x is what's called the independent variable. So that's called a one variable function because it's one independent variable. We'll see things like this, f of x comma y. That means x and y are both independent. So you call that a two variable function. Well, in this notation, if I want to take a derivative, I actually have two options now. I have x's and I have y's. I can do the derivative with respect to either variable. In Cal 1 over here, there was only one variable, so there was only one notation for derivative. We're going to have to specify which variable we're taking the derivative of now. So the way you do that, you change the notation some. Instead of using a prime sign, what we're going to say is f sub x. Okay, so that literally means the derivative or the partial derivative with respect to x. The reason they call it partial is because you can only do one or the other variable at a time. You can't do basically the whole thing. Okay, so that's basically equivalent to saying f prime of x in Cal 1. Likewise, we could have the derivative with respect to y, so that would be f sub y. Again, there's two different variables now, so you have two different first derivatives. In the other notation over here, instead of y equal, we'll typically would see they'll still use f of x comma y in our book equals whatever. Sometimes you might see it as z equal. But anyway, the notation that they're going to use is Leibniz notation, but instead of using a d like we did in Cal 1 over here, they use this fancy script d. So don't really think anything of it. df, that's the derivative of f with respect to x. Okay, so that's basically the same thing as saying f sub x. It's the same thing, just a different notation. You're going to see both notations on the homework and on the tests. F sub y, the same thing in Leibniz notation would be df over dy. Okay. So there we go. Again, if you see f sub x, that's the same as df over dx. If you see f sub y, that's the same as df over dy. That variable that they're listing in there is telling you what variable you're doing the derivative of. Now let's go one step further. In Cal 1, you got to second derivatives as well. We're going to have to do some of those here for what we need to do in the last section of the course. For the first notation here, you have f prime of x for a first derivative. F double prime of x would have been a second derivative. In Leibniz notation, you would have written this as the second derivative of y, like that, with respect to x. Oops, shouldn't use that fancy d there. with respect to x twice. That's basically what that's saying. So notice the y does not get the 2 on it, but the x on the bottom does. So that means both the first and second derivatives were done with respect to x. If you think about what a second derivative was, it was a derivative of the first derivative. Okay, so just like going from the original function to the first derivatives, we had 2 different ones over here on the right side of the screen. We could make the same argument when we go from f sub x down to second derivatives there. So what you would do is rewrite the first letter there. So I'm rewriting that x. That means my first derivative was done with respect to x. And then my second derivative, let's say it's also done with respect to x. So you'd get f sub double x. Now this actually has a really long drawn out way to say it. It would be something like the second order partial derivative with respect to x of the first partial order derivative with respect to x. I obviously don't expect you to say all that. F sub double x is perfectly fine. In addition to that, we could have done first derivative with respect to x, second with respect to y. Okay, that was a possibility. So just like coming from the original we did with respect to x and with respect to y, when I look at f sub x and go to second derivatives, I could do those with respect to x or y. Make the same argument over here with f sub y. So you could have f sub double y, and you could have f sub yx. And the reason I put an or there in the middle, one thing you should make a note of, those 2 derivatives are always the same. Okay. So yeah, it almost looks like we're doing 4 different second derivatives, but we're really not. There's really only 3. Because f sub xy, f sub yx should always come out to be exactly the same. To show you Leibniz notation, f sub double x would be this, the second derivative of f with respect to x twice. Okay. Likewise, let's go over here to the other end. Let's say you have the second derivative of f with respect to y twice. And then in the middle, you have, again, 2 options, because f sub xy and f sub yx are actually the same thing. We could write this as second derivative of f with respect to x and then with respect to y, or we could reverse that denominator. Don't get worried about what order x and y are on the bottom of that notation, because again it doesn't matter, because it's the same thing either way. That's why I have the or written there. Okay, so that's our notation. We want to look at some problems, so let's flip over here to Hawks. Okay, section 8.2, partial derivatives. First problem right there, 10x plus 7y equals 17. They want us to find, in step 1 here, the derivative with respect to x. Okay, so give me a second to write that down. Okay. So we've got 10x plus 7y plus 17. The question asks for df over dx. So that's the derivative with respect to x. So all I would ask you to do here is think about these 3 terms separately. If this were cal 1, and you had a function y equal 10x, and we said take the derivative, well, dy dx would be 10. Okay. All right. If you had 17, I'm skipping over the 7y for a second. If you had 17 and you were asked to take a derivative in cal 1, well, we know the derivative of any number is 0. go ahead and put that. Now here's the thing you've got to keep straight. That middle term, y equal 7y. Okay. I really probably shouldn't be using y here because again it's multivariable, but let's kind of ignore that for a minute. If I wanted to do a derivative there, what I want to think about is this. X is my variable. That means y is just a number. Okay, so you get that. Treat the other variable as a number. Treat y as a number. Okay. Well, if y is a number, then 7 times y is just a number. And we know the derivative of a number is 0. Okay. So you have 10 plus 0 plus 0, which is just 10. Alright, let's put that in. 10. There we go. Alright. Step 2, I should say. That you pretty much going to have 2 steps on all these questions. First step's always going to be derivative with respect to x. Second question will be derivative with respect to y. Okay, so again, we're still using that same function. But we want to do the derivative with respect to y now. Okay, so let me make some room here. What I like to do is just sort of start over. So I'm going to rewrite the original function over here. Okay, so derivative with respect to y. Okay, so everything is reversed here. Over here on the left side of the screen, when we did the derivative of 7y, that's where the other variable was, we got 0. So likewise, if y is our variable this time, if we do the derivative of 10x, we're going to get 0. In the middle term, derivative of 7y with respect to y would be 7. And the last term is a number, derivative of any number is 0. So you got 0 plus 7 plus 0, which would just be 7. Okay. Same sort of argument with this problem. I'm not going to write it out on the other screen. I'm just going to do it directly here. So this says the derivative with respect to x. So 17x squared would become, well, 17 times 2 is what, 34. That would be x to the first. And our second term doesn't have x. That means it's just a number. Derivative of a number is 0. We don't actually need to write plus 0. And in fact, it would count it wrong, I think, if I type plus 0. I mean, there's just really no reason to write plus 0. So there we go. Step 2, derivative with respect to y. So there's no y's in the first term, so its derivative is 0. Just do the power rule on the second term. Negative 13 times 3 be negative 39, and that's going to be y squared. Okay. There we go. All right, now we get into a little bit more complicated problems. Notice this problem compared to the last two problems, x and y were in separate terms. And this problem, look at this term I'm pointing at here, x and y are together in the same term. Same thing with the term after that. When that occurs, you've got a little bit more work you need to do. It's not really hard, it's just more work. What you need to remember from Cal 1 is something called the product rule. That was anytime you had something with x times something with x, You applied the product rule to get the derivative. The product rule was first times derivative of the second plus the second times the derivative of the first. We're going to actually have to do that same thing here. It's not x times x, it's x times y, but that's still product rule because it's a variable times a variable. That's really what we're looking at here. Alright, so there's our function. They want the derivative with respect to x. Okay. So if we look at that first term, x cubed, okay, that's derivative would be 3x squared. No big deal there. The second term there, let me write it out on the side here, 5x squared times y cubed. Think of this as 5x squared times y cubed like that with parentheses. So you could call 5x squared first and y cubed second. Remember the product rule was first derivative second plus second derivative first in Cal 1. Okay, so first is 5x squared. Derivative of the second would be 0 here because there's no x in the second part there. It's just y cubed, so it's just a number. So its derivative is 0 plus second, which is y cubed, times the derivative of the first. Well, anything times 0 is 0, so that's gone. If you multiply this out, you get 10x y cubed. Okay, so there's our second term. Okay. We'll do the same process in the third term here. So we've got 24x times y squared. Again, think of that as first times second. So first would be the 24x times the derivative of the second. So again, that second doesn't have any x's in it, so it's just a number. Its derivative is 0. Plus second, which is the y squared, times the derivative of the first. So the derivative of 24x would be 24. Well, 24x times 0 is gone. Y squared times 24 is just 24 y squared. And then your last term there is 6. That's just a number. We know the derivative of any number is 0. Okay, now what I've done here, I've used the product rule. This is the way the first way that Hawks shows you how to do it. There actually is, in my opinion, an easier way to think about this. Let me give you that. And if you like it, you can use it. Okay, so obviously our first term there, x cubed, becomes 3x squared when you do the derivative. Okay, no problem there. Let's concern ourselves with the second term, 5x squared y cubed. Keep in mind we're doing f sub x right now. Okay. This is literally 3 separate factors, a 5, an x squared, and a y cubed. Draw a line straight down underneath all 3 of those. Okay. Put a d for derivative on the variable you need to do the derivative of. So again, we're doing f sub x, derivative with respect to x. So I want the derivative of that. The other things can get brought down. So 5 gets brought down. I do the derivative of x squared and get 2x, and I bring y cubed down. So go ahead and multiply that out. That's 10x y cubed. And notice that's the same thing we got here. Okay, so again, this is just a different way to think about it. Let's look at the next term. 24x y squared. Same thing. Draw some lines under each factor there. 24 would come down. X is our variable. That's what I want to do the derivative of. I know the derivative of x is 1. And then y squared can come down. So if I multiply that out, I've got 24 y squared. There we go. Same thing. You'll see me do this in class because it's You know, again, in my opinion, it's a lot simpler to think about it this way. All right, let me go ahead and put that answer in. All right, there we go. And then let's go back and do the derivative with respect to y. So instead of rewriting all this, I'm just going to erase that derivative, and we can go from there. Alright, so derivative with respect to y this time. Our first term has no y's. It's 0. Second term, okay, let's draw lines down. Y is supposed to be my variable now, so I'm only going to do the derivative of the y part. 5 and x squared can come down. Derivative of y cubed is 3y squared. Okay. Next term, you got a 24, you got an x, you got a y squared. I'm only doing derivative of y's right now. So 24 comes down, x comes down. Derivative of y squared is 2y. And then our last term is just a number, so derivative is 0. Let's go ahead and clean that up. So 5 times 3 is 15. That'll be x squared y squared. 24 times 2 is 48 xy. So you can actually get away from having to do the product rule by using this little line method that I use. Okay, something with a radical sign. Remember, in calculus, we basically don't like radical signs. So first thing you always do, if you have a radical sign, change it over to where you're using exponents. So instead of y cubed times the square root of 9 plus x squared, we can think of this as y cubed times 9 plus x squared, all raised to the 1/2. Square root's the same as raising to 1/2. Alright. And that's the way I have it written here. Another slight difference here. Notice x is sort of buried in a parentheses that's all raised to an exponent. So there's only two factors here is what I'm trying to get at. There's the y cubed, and then all of this is a factor. 9 plus x squared to the 1/2. Okay, so if we're going to do the derivative with respect to x, y cubed just comes down. Okay. X is buried in this parentheses over here. So you got to go back to Cal 1 and think of a derivative rule that dealt with that. That would have been the chain rule or the general power rule. The way I taught my classes is we called it general power rule. So it was basically this: if I had f of x equal something with x raised to an exponent, let's say r for an exponent, then the way you took the derivative was move the exponent out front, so r went out front, rewrote what was in parentheses, exactly how it was, so I rewrite g of x, take away 1 from the exponent, and then multiply times the derivative of g of x. Okay, so that's called the general power rule. We could apply that here. So 1/2 could go out front. I could rewrite my parentheses, 9 plus x squared. Could subtract 1 from the exponent. 1/2 minus 1 will be negative 1/2. And then I need times g prime of x, so the derivative of what was in parentheses. Well, the derivative of 9 is 0. The derivative of x squared is 2x. Don't worry about simplifying. Perfectly fine to leave it like that. That's the way I'm going to leave it. We don't accomplish anything trying to simplify on these. Okay. There we go. Alright. Now if I had gone through the tutor button, they would have taken this further, they would have simplified, and they also, since this had a negative exponent, they would have ended up shoving it down to the denominator, and then they end up rewriting with a radical sign. You don't have to do all that. Just do the derivative and leave it. Okay? That's just as far as you need to go. Alright, and then part B, or step 2 I should say, the derivative with respect to y. So again, we just did derivatives with respect to x, so now we want to do derivatives with respect to y. Okay, so let me rewrite my function here. Y cubed times 9 plus x squared to the 1/2. Okay, I'm doing f sub y this time. Got my two factors there. I'm only doing the derivative of y though. Derivative of y cubed is 3y squared. This other term doesn't have y in it. I'm just going to bring it down. And done. So that one's real simple. Just derivative of y cubed basically. Oops. Alright, there we go. Okay, exponential function, let me mention one of those. In Cal 1, if you wanted to do the derivative of e raised to something, you would rewrite the whole thing and then multiply times the derivative of the exponent. Okay, so in other words, it was this. F of x equal e to the gx. Derivative would be rewrite it, multiply times the derivative of the exponent. And that was the rule. Okay, they ask us to do the derivative with respect to x here. So this is 5e to the x minus 4y. I'm going to rewrite it. And then I need to multiply times the derivative of the exponent. Okay, so I need the derivative of x minus 4y, but remember now, we're doing f sub x, so we need to do that with respect to x. Derivative of x is 1, the derivative of negative 4y would be 0, because there's no x in that term. Okay, so in essence, we just get 5e to the x minus 4y. Okay, and then the derivative with respect to y, same exact idea. I'm going to rewrite it, 5e to the x minus 4y. But when I do the derivative here, I need to do it with respect to y this time. So derivative of x would be 0. Derivative of negative 4y would be negative 4. You can leave it like that if you want. I'm going to go ahead and say 5 times negative 4 is negative 20. It's just a little bit less to type in. And that's simple enough to do. Oops. Careful with your signs. I just wrote plus instead of minus. Alright, and there we go. Alright, let's do a natural log. It's maybe been a minute since you've seen how to do a derivative of a log. So we've got 7x times the log of 4y. So here's the thing. When I say do the derivative of a log, I'm thinking back in Cal 1 where I have the log of something with x in it. Basically what you did there is you got a fraction. Bottom of the fraction is whatever you're taking the log of. I'm taking the log of g of x there. And the top was the derivative of the bottom. So g prime of x. That was the rule. But keep in mind, this rule's only going to apply if your variable right there is part of the log. So if I look at this function, I'm doing f sub x right now. X is not in the log, it's in front of the log. So do the line thing. Okay. Only derivative I'm doing is of x. 7 comes down, derivative of x is 1. Log of 4y comes down. Okay. So I get 7 log 4y. Okay. So I'm not even using the log rule for that part because x is not in the log. Alright, there we go. Alright, step 2, derivative with respect to y. Okay, that changes things. Y is our variable now, and y is in the log. So we're going to have to do this rule over here on the right side. Okay, 7 comes down, x comes down. The only derivative I'm doing is for the y, and it's buried in a log. So apply this rule over here on the right. So you get a fraction. The bottom of the fraction is what you're taking the log of. We're taking the log of 4y. And the top's the derivative of the bottom. Well, the derivative of 4y with respect to y would be 4. You can leave it like that if you want, but notice the 4's actually just cancel out. So you really just have 7x over y if you cancel those 4's out. Okay, and that's another log problem. That'll be the same process. I'll let you work that. Okay, I want to get over here. Same thing. Yeah, this is what I wanted to get to. Second derivatives. I mentioned those at the start of the video, but we hadn't done any in the homework yet. The second derivative questions will be 3-step questions. Step 1 will be f double x. Step 2 will be f double y. And step 3, they could either ask f sub xy or f sub yx, which we already know are the same thing. Okay, so in this one, we've got negative 9x squared y cubed plus x y to the 4th minus 6. And they want f double x. Okay, this is what we want. Well, we can't get to f double x until we get f sub x. So we've got to get f sub x first. They don't ask us for that, but we've got to do that to get to f sub double x. Alright, so I'm going to do the line thing. Negative 9 x squared y cubed. X is my variable. I'm doing the derivative of x squared. Everything else comes down. Next term, you got an x and a y to the 4th. I'm only doing the derivative of the x. So derivative of x is 1. Y to the 4th can come down. And our last term, it's just a number. And we know the derivative of any number is 0. Okay, so f sub x is, let's multiply this out. Negative 9 times 2 is negative 18 xy cubed. 1 times y to the 4th would be y to the 4th. Okay, so that's f sub x. The question asks for f sub double x. So now we need to take that and do the derivative with respect to x again. Okay, so negative 18 comes down, x comes down, y cubed comes down, and I don't know why I said comes down. I'm drawing lines under them. The only thing I'm doing the derivative of is x. So I got negative 18, root of x is 1, and I've got y cubed. Notice your last term there, y to the fourth does not have any x's, so its derivative is 0 because it's just a number. Let's go ahead and simplify to just negative 18 y cubed. Okay, there we go. Alright, step 2, f sub double y. Alright, so I'm going to rewrite my function over here on the right so I can draw down lines down beneath it. Okay, so let's see, f sub y. Again, I'm going to draw lines. Only difference this time, I'm doing derivative of y's. So negative 9 comes down, x squared comes down, derivative of y cubed is 3y squared. Next term, you got x and y to the fourth. I'm only doing the derivative of y's. X comes down, derivative of y to the fourth is 4y cubed. And our last term will be 0 because the derivative of any number is 0. Let's go ahead and multiply out. Negative 9 times 3 is negative 27, x squared, y squared. X times 4y cubed is 4 xy cubed. Incidentally, it doesn't matter which order you write x's and y's. I've just always written them x, y in that order. That's just a preference thing. I mean, if you write 4y cubed x, that would be fine. Okay, so that's f sub y. We need f sub double y. That's what we're looking for. Alright, so arrows again. I'm only doing the derivative of y's. Negative 27 comes down, x squared comes down, derivative of y squared is 2y. Next term, lines, 4 comes down, x comes down, derivative of y cubed is 3y squared. And let's go ahead and multiply out just for simplicity. Negative 54 x squared, y, 4 times 3 is 12, xy squared. Oops, x squared y plus 12 xy squared. Okay, there we go. And step 3, this is the last one, f sub xy. Okay, now they could just have easily have said f sub yx. Remember, f sub xy and f sub yx are the same. F sub xy equals f sub yx always. Okay, so you actually have two choices. You could look at f sub x and do the derivative with respect to y, or you could look at f sub y and do the derivative with respect to x. Either one should give you the same answer. Okay, so I'm going to go ahead and erase f sub double x because we don't need that anymore. I'm going to go ahead and erase f sub double y because we don't need that anymore. Alright, I've got my two first derivatives here. If I look at f sub x, I will need to do the derivative with respect to y, f sub xy. Okay, negative 18 could come down, x could come down, I'm only doing the derivative of y. So it's going to be a 3y squared there. Our next term, derivative of y to the fourth would be 4y cubed. And going ahead and simplifying, oops, negative 18 times 3 is negative, 54. So negative 54xy squared, and 4y cubed is already simplified. Okay, so that's what I get if I do f sub xy. If I do f sub yx over here, I should get the same thing. Let's just show that. If I'm doing f sub yx, I'm looking at f sub y, but I'm doing the derivative with respect to x. So x is what I'm doing derivatives of here. Negative 27 comes down. Derivative of x squared is 2x. Y squared comes down. Alright, next term, you got a 4, you got an x, you got a y cubed. I'm only doing the derivative of x's. So 4 comes down, derivative of x is 1, y cubed comes down. Go ahead and simplify. Negative 27 times 2 is negative 54. X, y squared. 4 times 1 is 4, so 4y cubed. And there we go. Got the same thing. Again, f sub xy, f sub yx are always the same. So it doesn't matter which one of them you do. You should get the same answer either way. Might be a good idea to do both of them and make sure you get the same thing both ways. Because if you don't get the same thing, you know at least one of them's wrong. You can go back and sort of look at your work. All right, so here we go. Negative 54 xy squared plus 4y cubed. And that was correct, and that was the last problem. So I only asked you the one problem with the second derivatives. Okay, practice on this because we're going to use it in 8.3 tomorrow. See y'all then.